chapter 3 of the course, we're going to talk about regular functions on some open subsets of affine varieties. And the big picture where we are in the course right now is that we have defined affine varieties and we already know what their Zariski topology is. And next, we start approaching the question, what are morphisms between such affine varieties? So if you have some background in category theory, the idea is that the affine varieties will be the object in some category, and now we need to define what the morphisms between them are. And this is probably also familiar from other parts of mathematics. And this definition, we want to have some features. So it should satisfy, first of all, that such a morphism in particular gives you a map of sets, because these affine varieties have underlying sets. It should be continuous in the Zariski topology that we just defined. But we have seen that these two would not be enough, because there can be pretty crazy maps from A1 to A1 in the Zariski topology. So they should satisfy something more. And whatever property we add in the end, we want this to be something that we can check locally on X. E.g., if you have an open cover of X, you want to be able to check on that open cover that you are a morphism. And this would be similar to other notions of morphisms in mathematics. So for example, you can check that a function is continuous on an open cover of the domain. You can check whether it's smooth, holomorphic, and so on. Everything are local conditions. And so these we keep in mind when we start approaching the easiest case of morphisms, namely morphisms to A1. That's basically the simplest non-trivial affine variety. And these things will be those regular functions in the title of the chapter. So when you look at morphisms from all of X, so from the entire affine variety to A1, it turns out that these will exactly be the polynomial functions f and a of x that we already have. But the twist that this chapter is about is that we also want to have morphisms on these open subsets of an affine variety, because, for example, we want to be able to check that something is a morphism on this open cover. So we need to understand what these morphisms are. And the central idea here is, let's say you're given this X, and then U inside there, which is the complement of some affine subvariety Y. So we want to define a function on the complement of this red part. And of course, if you are given the polynomial function on all of X, this will also give you, by restriction, a function on this open part. But you have a bit more freedom in this case, because, I mean, you can sometimes define functions on this open part which would not extend to a function on all of X. And how this happens is that, well, you can say, you look at the function phi from this open set to K, which should be given as not just by one polynomial function, but as a quotient of two polynomial functions. This still stays in the realm of commutative algebra. We can still describe this just using polynomials, but can now allow such a quotient. But then, of course, when you divide by something, you need to ensure that what you divide by is non-zero. And that is then the condition that this f of x should not vanish for all points on the open set U where you want to define your function. But if you ensure that, then you can allow such things. And you see, this is really the first time that we explicitly use that our target K, which has the values of the function, that this has this division. So that is the idea of the regular functions. You allow such quotients. And there's just one slight twist, namely, you want to make sure that the definition is local in this sense, that it can be checked locally on the cover. And this will require some small twist of this definition. But anyway. So that's what I just said. And so now we come to the definition of regular functions. So the input is that X is an affine variety and U is an open subset, and it's a Zariski topology of X. And then a regular function on U is first of all a map from U to K, which satisfies the following condition. So for every A in U, we can find an open subset, UA, which contains A and is contained in U. And then on this open subset, we find so polynomial functions f and g, such that f is non-zero for all x in this UA. And then the global function phi should be given on this open set UA as the quotient g of x divided by f of x. So that's the full definition. That's a regular function. So somehow, instead of saying that there should be one pair f comma g, such that on all of U, on all the parts, phi is given by g divided by f, you just say around every point on an even smaller open set, you must be given by such a function. At the end of the video, we're going to see an example where it really matters that you can restrict to such open sets. In any case, to finish the definition, the set of all such regular functions on U, we have a new notation. We denote this by curly OX of U. And we start with just some small observations and some conventions. So one thing that is not hard to see is that OX of U is a K algebra with pointwise addition and multiplication. So in other words, if you have two such phis, then their sum and their product are again regular. And also if you multiply by any constant in K, this again stays regular. And I mean, to check this, you can see it as a small exercise, but essentially the idea is that around each A, well, on one neighborhood, it's given by G1 divided by F1. On another neighborhood, it's given by G2 divided by F2, the second function. And then, for example, if you add the two functions, then, well, on the intersection of these two neighborhoods, they're given by G1 divided by F1 plus G2 divided by F2. And then you use the usual rules of adding fractions. And you see that it is then given still by a quotient of polynomial. So I think it's not a bad exercise to just write this down for yourself. Just once go through it so that you can make sure everything is fine. But probably it's not so surprising that you're allowed to add and multiply these functions. And kind of notation-wise, we will not always have this entire text here, but sometimes we just write phi is equal to g divided by f on UA as a shorthand for this equation here. And then when we write this, it looks really like we take one polynomial divided by the other polynomial in some kind of abstract ring sense. And I mean, from commutative algebra, this might remind you of this theory of localization. And be localizing at this function here, allowing it in the denominator. And I mean, that intuition would be correct. But we make this connection a bit later. So for now, this is really just kind of notation. And so that was the abstract definition. Let's see a few examples. We start with a kind of simple example, just to have something in mind. So on X equals A1, you have the open set where you exclude the 2 points 0 and 1. And then on that open set, let's see our first regular function. You can just take the function from U to K, which sends X to this fraction of two polynomials, so 3x squared plus 5 divided by X to the 2 times X minus 1. See, so this is the usual, again, I always sort of real picture, but this is the picture. And here we see this is a regular function because, I mean, it is the quotient of two polynomials, but it is not possible to extend this function on all of A1. So here we really use that we remove 2 points, and then we use this by allowing some poles along these points. But still, this is something we can describe with polynomials, and so we will allow this. And this is a special case where, in fact, for each A here, we can take UA to just be all of U, because here, globally, this function phi is given as the quotient of 2 polynomials. And the next example shows that this is not always possible. And there we have to go to slightly higher dimensions. So let's see again this affine variety x, which is given by the vanishing locus of x1, x4 minus x2, x3 inside A4. And then inside there we have an open subset, and the open subset is just to remove the vanishing locus of x2, x4. So you remove the locus where both of these things are 0. One thing you can see is that, in fact, this thing is completely contained in here, because when x2 and x4 are 0, then also this expression here is 0, because this vanishes because of x4, this because of x2. So this is really contained in there. And if we remove it, we get an open subset by the definition of the Tversky topology. And this, just writing it out, this is the set of all such 4 tuples, such that now either x2 is non-zero, or maybe also x4 is non-zero inside. And then we define a function from u to k, which sends this tuple here to some number, and we make a case distinction. So we see here this set, everything in x satisfies that either x2 or x4 is 0 when x are non-zero. So when x2 is non-zero, then we can write down the function x1 divided by x2. And if x4 is non-zero, we can write down x3 divided by x4. Okay, so this is, I claim this is a regular function on this open set U. The first thing we should check is that it's even a well-defined function, so that this doesn't give a contradiction. So in other words, what happens if both of those things are satisfied? x2 is non-zero and x4 is non-zero, because a priori we give 2 different formulas, but you can see these 2 formulas then agree, because, well, these are non-zero, so we can multiply by denominators, and if we do that, then we get this equation here, and that was exactly the equation cutting out x. So in fact, on every point of x, it's true that this equation holds, and therefore this equation holds. And so this definition doesn't give a contradiction, it gives a well-defined function to the base field k. And the other thing that is pretty obvious from this definition here is that phi is locally the quotient of polynomials, namely on an open cover of U given by U2, which is the locus where x2 is non-zero, and U4, the locus where x4 is non-zero. On this open cover, it's given by these two respective formulas. And then whenever you have any point in U, it must be either in here or in here, and then you can take that to be this UA, and this is the representation of phi on UA. So these 2 bullet points, this shows indeed phi is a regular function. And now the reason why we look at this example is that first of all, you see none of these 2 functions make sense on all of U. Sorry, this should be U. Because, well, you see that, for example, at the points 0, 0, 0, 1, first of all, this is a point in U, because, well, it's a point of x, because if you set the first 3 coordinates to be 0, then this expression, so this 0, so this equation vanishes, so it is a point in x. And it's also a point in U, because it is true that x4 is non-zero, and so that's a perfectly nice point here. But you see that this expression x1 divided by x2, this would give 0 divided by 0. This doesn't make sense. So at this point of view, this function here doesn't make sense. And similarly, you can exactly the same checks show that this is a point of view where this function doesn't make sense. So at least this shows that we can't use either this representation or this representation on all of you. And then a fact, which we won't prove, but which is true, is that there is no, this is not just because we're kind of unlucky with how exactly we chose the polynomials, but in fact, there's no presentation g divided by f as a quotient of polynomials, which makes sense on all of you. So this is the reason why we had to define in the definition of regular functions, why we had to say that just locally around each point in some neighborhood, we must be given by such a quotient. We couldn't just say, well, there's some global f and g which makes sense of all of you. Okay. And so, I mean, when looking at this example, I mean, there's all these equations and things are 0 or non-zero, and a priori it looks like a very artificial example, just to prove a point. But in fact, I wanted to show you that you can interpret this in a very natural way, these kind of vanishing sets. So they didn't just come out of thin air. I mean, these functions, in fact, make a lot of sense because let's see how to interpret this phi. And for this, the crucial idea is that this A4 with its 4 coordinates here, you can identify this as the set of 2 cross 2 matrices over K by arranging these x1 up to x4 in this 2 cross 2 matrix. And then if you look at x, the vanishing locus of this polynomial, well, this polynomial x1, x4 minus x2, x3, x1, x4 minus x2, x3, this is just the determinant of this matrix. And so this means this x is just the locus of all matrices which have vanishing determinant, or in other words, all the matrices whose rank is at most 1. Right? If it had full rank 2, then its determinant would be non-zero, and so the complement is exactly where the rank is less or equal 1. And then this open subset U, so this is x minus the vanishing of x2, x4. x2, x4, this is the second column vector. So in other words, if we remove this, then we'll only look at matrices such that the second column vector is non-zero. And then these two facts, m has rank less or equal 1, and the second vector is non-zero. This implies, well, that the span of the two column vectors has rank 1. The second one is non-zero, so this means the first one must be some multiple by some element of k of the second one. And then if you look at this function here, it was x1 divided by x2, if x2 is non-zero, x3 divided by x4, if this is non-zero. And you can just see, well, that dividing this by this will give you this number lambda if x2 is non-zero, and dividing x3 by x4 gives you the number lambda if x4 is non-zero. So in other words, this phi that we just defined is just this constant lambda, which we get told exists from just from linear algebra. So in other words, what we could check here is that this function sending a matrix in this open set to exactly this number lambda is a regular function. And I think that's a much more natural interpretation than just kind of staring at these quotients of polynomials. And that is something which might actually appear in some math problem that you want to solve. Okay, so this was the treatment of regular functions, and next we start studying their properties in more detail.